Hello, everyone. We have been talking about objects, bodies found in the universe, starting with the solar system, our system, and moving on last time to talk about the bodies found beyond the solar system, ending up with the whole universe and everything. We've talked about everything within the universe. Well, we talked about a lot of things within the universe, not everything. But today, here's what we're going to talk about. We're going to talk about distances to objects out there, distances from the Earth outward. So today, title, what we're going to talk about, distances. So distances. And to talk about distances, I want to make a table. We're going to start from where we live, Earth. We're going to move out, see what's out there. So let's put down a kind of like a table here. Let's put a line here. Let's put objects. Let's put the distance here in terms of something we might be used to, miles. Distance in terms of miles. And let's start our list. We're going to put some more things here too. So the first thing we're going to talk about this. From the Earth to our closest neighbor in space. What is the closest neighbor in space we have that we've actually walked on? It's the only other body out there besides the Earth that humans have walked on. Earth to moon. So we'll start off with that. What is the distance from the Earth to the moon in miles? You don't have to know this, but it's about 240,000 miles. Now let's come back to that. Let's just show what we're doing here. Let's, in this diagram here, let's show the sun. Let's show the orbit of Earth. So let's say here's the Earth going around the sun. Let's put the little Earth right over here. Label that Earth. And now we're going to show the moon. Here's the moon's orbit. It's not the moon, it's the moon's orbit. I'm going to put a little dot, green dot here. We'll call that moon. So we're talking about this distance right here. 240,000 miles. That's where we're going to start, from the Earth to the moon. And my question is this distance, 240,000 miles, is that a big distance? Now, I don't know what you're answering, but some people might be saying yes. Some people might be saying no. And you're both right. If whoever's saying yes is right, whoever's saying no is right. And why? Well, here's why. 240,000 miles. If I were to say between now and tomorrow, I would like you to go a distance of 240,000 miles. You would say to me, what are you talking about? There's no way. I mean, some of you have cars that have gone 240,000 miles, right? Or maybe are close. But hasn't it taken years to do that? Years. I mean, not something in a day. You're not going to go in your car and drive 240,000 miles in a day. I mean, that's crazy. Well, in that respect, that's a big number. It's a big number. Well, if I'm talking about everything out there, if we're talking about everything out there, isn't this distance going to be the smallest distance we're going to talk about? I mean, if we're going to go from the Earth to other places, it's going to be a bigger number than that. So this number, there's already a problem with this number. It is the smallest of the numbers we're going to talk about when dealing with miles. Is there a way we can write this a little differently? Well, yes. If we had 240,000 miles, is there a way in scientific notation we can write that? Here's what we do. We imagine a decimal right there, move this decimal over 1, 2, 3, 4, 5 places, and this becomes 2.4. If we move it over 5 places, tuck it between the 2 and the 4. Since we moved it over 5 places, isn't that 2.4 times 10 to the 5th miles? Some of you may have had this before, some of you may not. This is writing a number in scientific notation. That means you don't having to worry about the zeros. You get rid of the zeros. I mean, so 10 to the 5th is 2.4 times 10 to the 5th is 240,000 miles. It's just a more concise way to write it. But we're really not getting around the problem here. It's the same number. It's a number, it's a big number, and again, it's going to be the smallest distance that we talk about. So here's another way to say this. I'd like you to know about units a little bit. Now, here's a way for you to think about it. The units of miles are distance units. Have you ever been to, I'm sure you've been to Healdsburg on 101 or up north. Have you ever seen a sign, you know, those signs that say mileage, how far they are, the distance to cities? You ever seen a sign that says Hillsburg, 950,400 inches? You never see that. You don't see it written in inches. It's not written in inches. Why? Is that because it's inherently wrong? No, it's not necessarily wrong. It's because if you have a certain distance, you want units that are comparable to your distance, so you don't have to remember as many. So we have units like a mile. So instead of saying 950,400 inches to Hillsburg, it might say 14 miles or 20 kilometers. And you say, yeah, that makes sense to me. But 900-something thousand inches, that doesn't, because it's cumbersome. If you have a distance and you have a whole bunch of little units and have to remember a bunch of little units, so that's why we want units comparable to the distance. Kind of like this. Has anybody said to you, how tall are you? And you ever answer them, you say, I'm 300 millimeters tall. What, 300? 300 millimeters? What the heck? What are you talking about? 300 millimeters? That seems too tall. It's probably not 300 millimeters. But yeah, you see that, you don't express that in that way. You express like feet. If you're, let's 6 feet tall, you say, oh, I'm 6 feet tall. Someone understands that. Well, or if you say something like this, has anybody asked you how tall you are, and you say, well, I'm 0.0003 miles tall. You say, what? Well, it's not necessarily wrong. It's just that if you have a shorter distance, you want smaller units, not too small. So you want to have units that are comparable to your distance. That's what I'm talking about. So now, here's what we have to do. We have to come up with a new unit of distance in order to do this, because miles is just not going to cut it. When we're talking about millions, billions, trillions of miles, it's going to be too hard to remember numbers like that. So we have to come up with a new distance unit, a new distance unit. And to understand what this new distance unit is, how this works, we have to talk about the fastest thing there is. Does anybody know what the fastest thing there is? This is good to write down. The fastest thing there is light. That's not the new distance unit. I got to talk to you about this first. So we'll talk about what that distance unit is. It's not going to be miles. It's going to be something else. Does anybody know what the speed of light is? Light. Let's talk about the speed of light. The speed of light. What is it? Here's a number that I do want you to know. I'm going to write it in green here. The speed of light. It is, some of you might be guessing already, 186,000 miles per second. 186,000 miles a second. That is equivalent to also 300,000 kilometers per second. Kilometers per second. I want you to know this. I'm going to put a star here for both of these. This is fast. This is the fastest thing there is. Light is the fastest thing there is. Now, just to understand that, if I were to take a laser beam, here's a laser, and I shine light out of this laser. Now, the light hits the paper almost instantly. It's very close to the paper. But let's say I pointed this laser beam over at the wall. You're not seeing that, but if I'm pointing this laser over at the wall and turning it on, well, that light almost, it's fast. It's just like turning on a flashlight. Well, what if that wall weren't there? What if the laser went straight? And if you shine this laser at a wall, but let's say the laser didn't hit the wall, it just kept going, and it didn't even go into space. There was nothing in the way. And imagine it orbited around the Earth. When would it come back to the other side of the laser? So if the light comes out here, when would it come back and hit here? All the way around the Earth. You know when? As soon as you turn this laser on, in a 1/7 of a second. 1/7 of a second. That's crazy. You couldn't even get a shot off in basketball. That's like 0.143 seconds. You can't, if someone passed you a basketball and said, get off a shot in 143 seconds, you can't even do that. Actually, in 0.3 seconds, they're not even, in a basketball game, when you have 0.3 seconds, you can't catch and shoot. It's not enough time to get a ball, catching the ball out of your hand. So as soon as I turn this laser on, within 0.143 seconds, it comes back and hits there. That's fast. You know what that means? 7 times around the Earth in a second. If you were to let a second pass, it would go around the light would go around the Earth 7 times. 7 times in a second. That's the same as 186,000 miles a second. That's the fastest thing there is. Now, we haven't gotten our new distance unit yet. Have not, but we're about to. Take a look at this. We're going to do an experiment. So in our experiment, I'm going to put our assistant down here. I can't really draw our, people well, but I can draw our assistant Joe pretty well. This is how, well, as my interpretation, I can't draw. You should be able to tell that already. My dad was a good artist. I can't draw. So here's Joe. And what I'm going to give Joe, and if you do see Joe, you'll recognize him. That's Joe, our assistant. And what we're going to do is give Joe a flashlight. He's holding a flashlight in his hand. There's a flashlight. If you're not sure what that is, write this, flashlight. Flashlight. So what Joe's going to turn on this flashlight, and we have another assistant way over here by the name of John. That's not the way John looks. Now, he's my assistant for my other class. So there's John, and what John has, he doesn't have a flashlight, he has a stopwatch. What he's going to do is he's going to time. He's going to time the light from when Joe turns it on to when he sees the light. But something I need to tell you is this. The distance from Joe to John is 186,000 miles. That's the distance. Which means this. As soon as Joe turns on the light, John's going to be ready for it. John's going to be actually looking at his stopwatch. He's going to know. Joe told him when he's going to turn the light on. John's looking at his stopwatch and says, okay, Joe's going to turn on the light right now. So Joe turns on the light. Here comes the light. Light heads out. John sees the light. John stops the stopwatch. Can you guess how long it took that light to go from Joe to John? And maybe you guessed it. That light took 1 second. Well, for those of you who guessed it, how come you knew that? Well, doesn't light travel 186,000 miles per second? So if light travels 186,000 miles per second, that means in 1 second it's going to go a distance of 186,000 miles. So we're coming to our new distance unit. Here's what it is. Instead of calling this distance 186,000 miles, we're going to call this distance 1 light second, a new distance unit. A light second would be equal to the distance, not time, it's not a time. It's the distance light travels in 1 second. I'd like you to know that. A light second. You say, oh, light second, that seems like time. Well, it's only because you're used to the word second being time. But if you put the word light in front of it, it becomes a distance. A light second, the distance light travels in 1 second. I'd like you to know that. So now look at this. Instead of writing 186,000 miles, you can write 1 light second. Isn't it easier to remember the number 1 than 186,000? I bet you used the word, I bet you said the number 1 today at some point. I bet you didn't say 186,000 at any point today until maybe we wrote it down here. So it's a less cumbersome way to write this distance. Instead of miles, you write it in light seconds, 1 light second. Well, let's think about this. What if John and Joe were separated by twice that distance? Wouldn't it be 372,000 miles? What's another way you can say it? 2 light seconds. 2 light seconds would be the distance light travels in 2 seconds. You could say 372,000 miles. We could say 2 light seconds. What if they were separated by 60 times that distance? It would be some number of million miles. Or what if you could say 60 light seconds? Oh, but wait a second here. Isn't 60 light seconds the distance light travels in 60 seconds? Don't we have another word for 60 seconds? A minute. So 60 light seconds equals 1 light minute. A light minute is the distance light travels in a minute. You see how that works? Isn't that easier to say? I mean, that's an easy way to say it. You let a beam of light travel for 1 minute. You know how far it's gone? 1 light minute. You don't even have to calculate how many miles that is. It's a lot. Well, if you have light minutes, couldn't you have light hours? The distance light travels in an hour? Wow, that's interesting. You have a light hour. Couldn't you have a light day? The distance light travels in a day? Yeah, I guess so, a light day. Couldn't you have a light week? Couldn't you have a light month? Couldn't you have a light year? Couldn't you have a light century? Well, you all heard of light years before, right? What a light year is. Well, a light year is the distance light travels in a year. You know what that is in miles? It's almost 6 trillion miles. Isn't it easier to remember 1 light year than 6 trillion miles? It is. So now, you have an idea of these new distance units that make things less cumbersome if you're talking about really big distances. So let's go back to our original page here where we're going to list these bodies. Let's put another column here. Let's put it as far as distance in light travel units. All right? Well, take a look at this. 240,000 miles. Isn't that, if this were 186,000 miles, wouldn't we say 1 light second? But isn't it a little bit more? Well, that's not a problem. 1.3 light seconds. You don't have to know that. But the moon is at a distance of 1.3 light seconds. Because it takes light 1.3 seconds in time to go from there to here, from here to there. So if you shine a flashlight at the moon right now, the light gets there in 1.3 seconds. If the moon were to blow up right now, don't worry, the moon is not going to blow up. There's nothing around here that could blow up the moon, like the Death Star could blow up the moon, but the Death Star is not around here. If the moon blows up right now, and you're looking at it, you'd say, oh, there it goes. It would be 1.3 seconds later after it blew up that you'd see the explosion. You know what that means? When you look at the moon, you're seeing it back in time, 1.3 seconds. Actually, when you look at anything, you're seeing those things back in time. But does it really matter if you're looking at your computer or the person next to you? No. The back in time is just a fraction of a second. But when you look farther out there, it makes a difference. It makes a difference the farther you look out there. The farther you look out, the farther back in time you're seeing. Well, now, let's put another column here. Some of you have gone 100 miles an hour in a car. I'm not recommending that, but maybe you have the feeling for doing that. You should not do that. It's not safe, plus if you get stopped, you're in trouble. Yeah, but even if you've gone 80 miles an hour, you're close to 100 miles an hour, right? If you haven't driven 100. So let's talk about the time to get there at 100 miles per hour. Well, and you know, these numbers so far, you don't have to know these numbers. I'm just kind of giving you something to think about. Well, you know how long it would take you if you went 100 miles an hour nonstop, road to the moon? It would take you 3 months, which is 1/4 year. Now, how many would do that? How many would do that? Anybody? Okay. Maybe some of you would, because you know you want to go there, but I mean, and you have to come back. You don't want to stay there. That would be 6 months out of your life. Let's say I give you an RV. You don't have to go in your own car. You can go like in an RV with like a satellite TV, food stocked, refrigerator stocked with whatever food you want. I mean, old Chicago pizza, Thai food. I mean, and you think of it. I mean, as much whatever you have burritos every night. I mean, anything, Chinese food, anything. Would you do it? Okay, I'll sweeten the pot. And some of you probably would. What about this? What about I give you Mike Trout's new contract, over $400 million that you get to spend. You get it all at once, tax-free. Even Trout doesn't get that. And you get it when you get back. Would you do that? I bet a lot of you would, even if you wouldn't. Okay, in the RV, you could take anybody you want, whether they like it or not. Would you do it? Okay, I bet a lot of you would. I would. Hey, that would be awesome. I mean, when you get back, you have all this money. It's only 6 months out of your life. You get a nice RV to spend, and it's a good vacation. It is a good vacation. Well, okay. Some of you, I bet a lot of you would. I wish I could see who would. And maybe some of you wouldn't, but I bet a lot of you would. Now, take a look what you've just done. You've gone from the Earth to the moon and back. You've gone this, which is nothing. That's all you've done. Let's go somewhere else. Let me show you the closest planet that gets to the Earth. Now, some people say Mars, as far as major planet. And actually, you know what? There's a planet, and I'll show this. That's Mercury right over here. Let's say this is Mercury. There's a planet that gets relatively close to the Earth, relatively close. The planet Venus. Right there. There's Venus. Venus gets to within 25 million miles of the Earth. So let's do this. Let's go from Earth to Venus, which is about 25 million miles. You don't have to know that. Nothing on here do you have to know. You don't have to remember this. I'm not going to ask you that stuff. I mean, I will ask you, like, what the speed of light is. That's good to know. Okay, maybe I'll start writing things in, if I write it in green, know it. I mean, still, I might ask you something else, but for sure, green means no. Know it if it's in green. Look, it's green. You see it? Means no. So I put a little asterisk there. Asterisk, know it. Green, know it. For today and even last time, for sure, green. You should know it. Asterisk, know it. All right, that's the rule for today. Important. All right, 25 million miles. You know what this is? This is approximately 100 times the Earth. There's a symbol for the Earth to moon, little crescent moon distance. So instead of being 1.3 light seconds, it's 130 light seconds. So Venus, when it's closest, that's when it's closest. I mean, it's not always that distance. That's when it's closest. It's only 130 light seconds. Wait a second, 130 light seconds. Doesn't that mean the distance light travels in 130 seconds? What is that, close to 120 light seconds? But if you have 120 light seconds, right, at that distance, isn't it the same as approximately just over 2 light minutes? When you see Venus, you ever see, over the last few months, I mean, you've probably had plenty of time to go out and look at things. Do you remember something really bright when the sun set? Not the sun. Don't look at the sun. It's something that, well, after the sun set, the bright thing. Could have been the moon, but if it was a star-like object, it was actually a planet, the planet Venus. Venus, when you look at it, you're looking at it the way it looked 2 minutes ago. You're looking back in time 2 minutes. If Venus were to blow up right now, again, don't worry about that. Nothing's going to do that. You'd still see it for 2 minutes before you saw the explosion. And it's kind of weird. But that's what happens when you're dealing with very great distances. Now, what about time to get there at 100 miles an hour? It would be 100 times a quarter, 25 years. Imagine being in your car 25 years nonstop at 100 miles an hour. You go the distance of Venus. You wouldn't want to do that. Now, some people would. I mean, would you for Trout's contract, for whatever food you want, for an RV, 25 years? And remember, you have to come back. You don't want to stay at Venus. Venus is not a nice place. I don't know if you'd want to go there. Because guess what? I'll tell you right now, since we're not going to talk about Venus in this class very much, Venus is hot. During the day, it's 900 degrees Fahrenheit. You can't go out. You can't go out and play. You know how the hot days, you kind of wait to go out and play? You can't ever go out and play. It's too hot. Now, you might say, oh, if I wait till it's night around here, sometimes you get evening, night. You know, if you want to go out, you can go out. Venus at night, 850 degrees Fahrenheit. You still can't go out. You can't sleep in a temperature like that. 850 degrees Fahrenheit? It's too hot. With fans blowing on you, it doesn't help. So it's too hot. So that's, and it's even worse than that. The atmosphere, there's not oxygen to breathe. It's all CO2. You'd suffocate. You can't go out. If you go outside and it's really hot, you couldn't even breathe. Yeah, you'd suffocate. You couldn't breathe there. Plus, the nice clouds that it's covered with, they're made of sulfuric acid. Even going through the clouds, sulfuric acid is not good for your skin. It's not good for you. You don't have sulfuric acid on you. You remember, kind of like alien blood? Remember Alien? What happens? You don't want that stuff on you. It's not good for you. It's not good for, it's not good at all. Well, there's even something worse than that. The pressure's so high on Venus that if you were on the surface, it would be like being underneath the ocean, almost a mile deep. You know what happens? You get crushed. The atmospheric pressure is 90 times Earth's atmospheric pressure. You'd be crushed into a baseball. So you'd be crushed, you'd suffocate, you'd have acid on you going through the clouds, and you'd burn up all at once. And I've heard that's not a very good experience. So you're not going to like Venus. It's like the worst place in the solar system, the absolute worst. Let's go somewhere better, which is anywhere. Look at this. Earth to the sun. Let's do that. Earth to sun. Now here is finally a number I'd like you to know. 93 million miles. We'll talk about that. Well, you might say, wait, Earth to sun? How is that better than Venus? Well, there's only one thing that happens to you as you get towards the sun. What happens? You burn. You burn up. Oh, you go into Venus, you burn up, you can't breathe, there's acid, you get crushed. At least in the sun, you just burn up. It's actually a nicer vacation spot than Venus. So if you pick between Venus and the sun, go to the sun. You really shouldn't pick either. But if you had to make a choice, sun. Sun a better place than Venus. Now, I said 93 million miles that you need to know. Well, yeah, here's why. Let me come back here. because it is a very special distance talking about things in the solar system. It is the average Earth to Sun distance. We'll write this down again. We'll put it right below here. 93 million miles is the average distance from Earth to Sun. It's good to know. You know what? Instead of writing it in green, I'm circling in green. Like, so the rule applies. If there's not circle, a box in green, rectangled it in green, I'll put an asterisk there. This is also called something. It's the average distance from Earth to Sun. It is known as some of you might know this, astronomical unit, or 1 AU. That is good to know too. I'll put a box there. I might ask you that on a quiz the next day after you see this, if you see this the day you're supposed to. 1 astronomical unit. An AU is a very appropriate distance in the solar system to talk about distant objects, Earth to the Moon. Earth to the Moon is not maybe the best, but from the Sun to different planets. Sun to different planets, AUs. They use AUs all the time. In this class, we're not going to use AUs very much. But it's a good thing to know. An AU is an astronomical unit. It is the 93 million miles average distance from the Earth to the Sun. Well, now, pretend we go to the Sun. 93 million miles. This is approximately 4 times, again, 93 million miles is good, but again, you don't have to remember all this other stuff. It is approximately 4 times the Earth to, there's a symbol for Venus, distance. So instead of 2 light minutes, 8 light minutes. The Sun is about 8 light minutes from us. That means if the Sun were to blow up right now, for how much longer will we have fun? 8 minutes. No, actually, the semester would be over. You get to have a shortened semester. So the Sun is a distance of 8 light minutes. You're seeing the Sun back in time, 8 minutes. And here's something interesting. If the Sun were to be taken away now, nothing's going to take away the Sun. Don't worry about that. But if some creature, some being out there took the Sun and made it disappear. Now, the Earth's orbiting the Sun. What would the Earth do at the instant the Sun disappeared? Guess. Well, guess what the Earth would do now? Now you think, hey, if you're spinning a rock on a string and you let go of the string, the rock's just going to fly off instantly. Well, guess what? The Earth orbits around nothing for 8 minutes until it gets the message that the Sun's not there, and then it flies off. It's not good for the Earth. Not having the Sun there, flying off is not the problem for the Earth. Not having the Sun, that's the problem. Yeah, we need the Sun. Well, don't worry about this, but what I'm trying to say is here, gravity waves, the effect of gravity work at the same rate as the speed of light, which is interesting. We'll talk about relativity and that, so we'll talk about that. Well, now, 8 light minutes. So let's talk about this. What about going there? If it's 4 times the Earth to Venus distance, it would be 100 years. Think about being in your car at 100 miles an hour, 100 years, nonstop. You've gone the distance of the Sun. Now, I'm not going to even ask you. I bet not many people would want to do this, especially if you weren't going to do this. Well, then again, Sun's nicer, but it takes longer to get there. Actually, I don't blame you if you don't want to do either of those. I mean, Moon, reasonable. That's not reasonable. Now, let's go somewhere, the last part of the sheet here. Let's go somewhere that's the most bad-mouthed thing in the solar system, most ridiculed, was demoted. Let's go, just to kind of like make it feel a little better. Let's go, since we're at the Sun now, let's go from the Sun to Pluto. Instead of the Earth to Pluto, let's go from the Sun. Imagine we have Pluto way over here. Let's put Pluto over here. Pluto. P for Pluto. Sun to Pluto. Let's take a look at these distances. This is 4 billion miles. You don't have to know that. This is approximately 40 Earth. There's a symbol for the Sun. Circle with a little dot in it. Distances. Wait, 40 Earth-Sun distances. What did we just say an Earth-Sun distance is called? Yeah, about 40 AU. You don't have to know that. So now, look at this. If it's 40 Earth to Sun distances, 40 times 8, 320 light minutes. Oh, hold on here. This is kind of like, I can't even visualize this. It means that Pluto is at a distance of 320 light minutes. Well, isn't this about 300 light minutes? Or 320, about 300. Well, isn't there a better way to say 300 light minutes? 300 light minutes is the distance light travels in 300 minutes. But 300 minutes is the same as, isn't it the same as 5 hours? Approximately 5 light hours. If you were to see Pluto, and I've seen, I think, a couple times in a scope, it's hard to tell. You're seeing Pluto not the way it looks right now. You're seeing Pluto the way it looked 5 hours ago. When we got a spacecraft to Pluto, finally in about 2015, called New Horizons, it sent the signal back to us, the pictures of Pluto in form of radio waves, how we communicate with cell phones and TV, a lot of radio waves. Well, the signal took 5 hours to get back to us. Radio waves travel at the speed of light. There's a different type of light. So if you were out at Pluto and wanted to talk to your friend on Earth and have a phone, it would take you 5 hours to after you say hello for your friend to get the message. So that's pretty far. And that's far. But we're still in the solar system. We're still part of the solar system. There's still more of the solar system. Remember the Kuiper belt there, even the Oort clouds? We're still in the solar system. Well, now, look at this. Instead of 100 years, be 40 times that, 4,000 years. 4,000 years. If you wanted to get in your car, hop in, load it up, or your RV, and head off to Pluto at 100 miles an hour, and can drive through space, take you 4,000 years. You have better things to do than that. So again, if you didn't want to do this or this, I don't really think anybody's going to want to do this, because you're really not going to want it. Pluto's cold. It's not a nice place. It's nicer than Venus, but it's still not that nice. So, and look, I just want you to get a feel for the distances, and we're just talking about the solar system. Now, later on, actually, you know what? I'm going to post a video for you. This is about I think it's about a 10-minute long video, 8-minute long, about some guys who had nothing better to do than to go out. It's a great video. They did a really good job to go out into the desert and to make a scale model of just the solar system, a scale model using like lights. And I mean, it's really well done. They use some good music in it. So I'm going to post that video to go along with this. And the next day, tomorrow's, the last two lectures that you saw, this one and the previous, will be, well, it's good to know. I was going to say something, but I don't need to say it. Of course, you're going to be tested on that. So good stuff to know. And that is it. And until next time, signing off. And we'll see what's going to be in store next time. More distances.